afternoon to all. Myself Joshi SS, Assistant Professor, Mechanical Engineering Department, College of Engineering, Muttathra. I would like to welcome all the participants to the final day of our ATAL-FDP on Green Energy Solutions, Building a Sustainable Carbon Neutral World, conducted by Mechanical Engineering Department, College of Engineering, Muttathra. Today's topic is the welcome synergy of smart grid, renewable energy and power electronics, advancing sustainable energy integration, and is chaired by Dr. K. Deepa, Associate Professor, Amrita Vishwavidyapeetham, Bangalore. Dr. Deepa has doctorate in power electronics and drives and having more than 26 years experience in teaching, and she is specialized in machine learning, artificial intelligence and renewable energy technology. I welcome Dr. Deepa to start the session. Ma'am.
Thank you. Thank you, Joshi sir. Good afternoon, one and all present here. I thank CEM for organizing this ATAL-FDP, and I thank them for giving me this opportunity. Special thanks to the HOD for giving this opportunity, and Sonishar for helping me in presenting this PPT. Now, this particular presentation is just in a way arranged to give the introduction about what is sustainability, the role of renewables energy over there, and the role of power electronics, and what electric vehicle does over there. And in the middle, I would have try to incorporate the works done under my guidance from my students, so that it gives a feel of the research what is happening out in India. So sustainable is a word which is the buzzword which is there in each and every topic over here. So what is the importance of sustainable energy? Now, the first and the foremost, all the sustainable name came out only because of this global climatic change and the environmental concern. And the next thing is we are dependent on to fossil fuels, and because of which carbon emissions are more. And now as exactly driving out to the topic of the FDP, which is carbon neutral, carbon zero. So we are trying to move on from fossil fuels to the renewable energies, so that we are going for carbon zero. And this also ensures security for the future generation, and in turn we have economical development as well as energy equality between the world, all throughout the world. Next, we will just see what is the roles of smart grids, renewables and power electronics. What exactly is a smart grid? Smart grid, as the name indicates, smart grid is intelligent. It can decide something by itself. So it has to decide how much should be the energy produced tomorrow, and what would be the load tomorrow. Tomorrow might be one industry might be shut off, and so the power needed by that industry is zero. At the same time, the input has to be also reduced because of this load condition. So there should be a match between the supply and the load, and hence smart grids plays an important role in energy distribution between the source and the load. And this smart grids has source taken from many different sources. It could be from some fossil fuel sources plus renewable energies also. Renewable energies, when we are talking about, it becomes solar, wind, biomass, etc. So all these put together onto a single grid becomes a smart grid with intelligent features. So renewable is a part and parcel of the smart grids. And when we are bringing in a constant source, which is a fossil fuel source, and an intermittent source. Solar, wind are not constant in nature, they are intermittent. So when we are bringing a constant and an intermittent source, then there should be a match between the power levels, and hence power electronic devices come into picture. They are just switching devices which balances the energy between the sources and the load. So these are the major components of a smart grid, and the main aim of this particular thing is to move on to net zero and electrification goals, and to enhance the reliability and sustainability of the systems. So going on to the next step, which would be the definitions and the features. Advanced energy systems, it should have two-way communication. It is not just a one-way communication where it communicates and tells that this is the amount of the source available and it has to be used. It depends on to the load also. We should be knowing what is the load, and accordingly the source has to be split between the loads. So it is a two-way communication protocol between the source, load, and as well as the controlling devices. And it has self-healing capacity for enhanced reliability. There is a buzzword which is often called as peak load condition. Maybe during the afternoons, the total amount of power needed is going to be more, which is called as a peak load condition. During that particular condition, we will have to map the renewable energies to the load more. And if there is any fault occurrence, then that particular network, that particular source would be removed, and the other sources would be taking up the position of the removed source. So there is something which is intelligence bringing into picture, which also brings in self-healing capacity. For all these things, real-time monitoring of energy is needed from the source as well as from the load side. So hence, real-time energy monitoring has to be there, and as well as the load, which is nothing but demand response, also should be known to us. And all these renewable energies, along with the battery source, are called as distributed energy sources, such as solar panel with a battery, wind, or it could be biomass. All these are distributed energies. These distributed energies are brought into the smart grids wherever it is available. So, and hence an efficient balance between this and dynamicity has to be balanced. And so these are the things which you have to know about a smart grid. Now, to make a system intelligent, then we should feed some feedbacks to the controller. So those feedbacks are always taken from the sensors. So these smart grids would be having many sensors which measures the grid performance, like it could be current, voltage, power levels, or for stability we would be measuring many other things, and for safety also we will be monitoring through the sensors. So sensors are important, or the first eye, or we call this as eye of the network, which monitors all the parameters and gives the feedback for controller to control the parameters. And once when the controller decides something to be performed, then the controller inputs has to be taken back to the concerned equipment for controlling, and this is done with communication network. So control signals has to move on to the correct equipment, and it has to switch on or switch off, or some safety devices has to be switched on accordingly. And hence next comes the communication network, which ensures real-time data flow between the components. And previously, as I told, the sensor input has been taken into the controller, where control systems plays a major role over there in the controllers, and the output of the control systems would be taken through the communication network, either for storing the energy or for retrieving the energies from the energy storage systems, which are nothing but backup system, because we all know solar is intermittent in nature. It will be available only during the daytime. Suppose if you need the energy during the night, then it has to be stored in a battery source, and that becomes an energy storage. So everywhere energy has to be balanced. Energy balance between the renewables and the fossil fuel based sources, energy balance between the sources and the load, energy balance between the renewable energy sources and the energy storage device is important. So integrating these things together effectively and intelligently becomes a smart grid. So the benefits we all know, because the current day India is totally dependent on renewable energy sources now. It reduces the energy losses during transmission and distribution. We need not transfer power very long distance. Previously, power used to be transferred thousands of kilometers to reach the rural areas. Now smart grids can be placed wherever renewable energies are available. And hence, since the power has been produced at a very short distance, losses are lesser in transmission and distribution. The overall grid reliability and resilience are being improved against outages. Previously, we would have seen in rural areas, we would have not got much power and we will have more of outages. Maybe in cities like Bangalore, Chennai, or Trivandrum, you will not have power cuts, but when we go in interior towards any village, the power outages will be more because the total power would have been shifted to a cosmopolitan or a metropolitan cities. Villages would be affected or rural areas would be affected. But because of smart grids, those problems can be overcome. So enabling the it gives us a provision for adding more renewable sources. And it empowers the customers to use the real-time data and cost savings. It also builds the fundamentals of future energy markets and systems, because future it is going to be totally dependent on to smart grids, because we all know electric vehicles are already on the roads, and if all the as per Indian government's view, at 2030 we are going to have 30% of all the vehicles, be it a heavy bed truck or any of that particular sort, or two-wheelers, three-wheelers, 30% of it is going to be electric vehicles. So in that particular case, we needed more amount of energy, where smart grids would be the only option which has to be taken up. These are some of the examples which have been noted down from the internet. So one is California, USA, where the integration of solar and EV is a very good case study to be taken up. And in Europe, if we are talking about, we have wind energy more in Europe, and wind energy projects linked in with smart grids is one of the case study which can be taken up. In Japan, where the disasters is always more over there, microgrids are the only options in disaster prone areas, and smart grids always focus on energy efficiency and reliability. And talking about India, we have My City, which is a major hit in Mysore, where solar is the major thing. And in due course of time, 6 months ago, there was an article stating that solar produced by the Mysuru residents were more than what is expected from the load side. So this is the status of India now. So renewable energies, as I told already, it is solar, wind, biomass, hydropowers, etc. And the main reason for introducing renewables more into the system is to reduce the carbon footprints. So the challenge is when we are bringing in a renewable energy sources. Now, as I told in the initial thing, we have a rigid source which is nothing but a fossil fuel based source. Maybe it is hydrothermal based systems, thermal systems, etc. So those are constant sources. They produce the power at a constant rate. There is no intermittency over there. Whereas when we are talking about a renewable energy sources, this is weather dependent. For solar power, sunlight is important. So rainy days or cloudy days would reduce the amount of solar energy. And when it is during the night time, again, the amount of energy produced is lesser. Wind, again, it is dependent on to the speed of the wind, cloudy days, etc. When you have a constant source and an intermittent source, which has many peaks, when you are paralleling these two things, we'll have many challenges because voltages has to be mapped. A basics of electrical is when you're paralleling two systems, voltages has to be the same. When voltage is fluctuating in one of the device, then when we are paralleling it, then the device with the least voltage would be affected. And hence, this is a major concern when you are paralleling a renewable energy source to the grid. So in this particular place, a power electronic device comes into picture, which tries to maintain the voltage when it has been paralleled. So these are some of the drawbacks in connecting a renewables to the smart grid. Smart grids are solving this renewable energy issues. As it is having intelligence, it automatically brings in the source or a capacitor or an inductor to nullify the effect of a reduction in power or the increase in power. So smart grid is one of the solution for the problems which are being stated in renewable energies. Now, these are the case studies of renewable integrations. One in Denmark, we have many in India, Germany, etc. Now, how does power electronics play a role over here? We all know that basics is DC to AC is an inverter and AC to DC is a rectifier. So we have two types of sources now, which is one is analog alternating source and the other is DC. So AC and DC both would be available in a smart grid. So how are we going to compare these things or convert one from the other, it is through your power electronic devices. The key converters would be any of these converters, DC-DC converters or DC-AC converters or DC-AC to DC converters. We have a common block diagram which tells us the basics about the importance of power electronic devices. We might have the source in any one particular form. It could be AC or it could be DC. Then the load would be expecting AC or DC. Suppose if the input is AC and the load is requiring DC, then I'll have to go in for taking out a power converter, which would be converting AC to DC, or the reverse. So hence a power converter is placed in between the input and the output. And this power converter has to be controlled by a controller, which takes in the input from the output and accordingly maintains the voltage or current levels depending on to the necessity. So this power electronic systems not only helps in energy conversion, as I told, AC to DC or DC to AC, or DC to DC itself. Sometimes if I have solar energy 24 volts available and I wanted 5 volts for charging a battery or something, 5-volt battery, then we needed a DC-DC charger over there. So this is not only for power conversion, but it also maintains the power quality and it also reduces losses. Whenever we are adding any laptops into the systems, it is decreasing the power quality of the system. It increases the harmonic, and hence power electronic devices would be a major part of reducing the harmonics and increasing the power quality. So we have some of the power electronic inverters, wind turbine converters, EV chargers, which are in action already. And so this plays a major role for sustainability. So there are many innovations in power electronic devices. Initially, it started off with diodes, thyristors, and MOSFETs, IGBTs. Now we are moving on to silicon carbide and gallium nitride devices. So these are modern devices. The main purpose of taking up these devices is to increase the efficiency, because the losses are very less in these devices, and also the size of the devices are very, very less, and hence we are able to make up compact designs. Because when we are talking about any device in electric vehicle, the size is more important, the weight is more important. Or if you're talking about a power converter in space application, weight of that application is more important. So there, if we are going to replace the previous used switches with silicon carbide and gallium nitride, we would definitely get a higher efficiency to reduce the weight of the systems. And many smart converters have come in, which is with IoT based AI or machine learning based systems. So nowadays, these buzzwords of IoT, AI, and ML are used for controlling the converters so that it is automatic. As we told, it takes its action by itself. And many other innovations are being done with modular designs and for increasing the lifespan of the systems. This is one of the work which is being carried out by my PhD scholar. To just have a link with the EV chargers, what we told, this is a perfect example. This is an EV charger, which is converting DC of one voltage to DC of the other voltage. And we have the citation given below so that you can have a detailed explanations there. This is a 10 kilowatt system. And this 10 kilowatt system is designed for reducing the voltage of input voltage from 800 volts to 500 volts. So the corresponding switching frequencies and the MOSFET used is being given over here. This particular charger was being designed, and the converter was with the TMS kit. The converter was a PWM converter, which was being implemented with the TMS kit. And the load variation was being verified, the load regulation was being verified, and this has been given in the tabular column. And you could see over there for a change of 25 volts to 100 ohms, 25 ohms to 100 ohms, you can see that it is settling out within a fraction of milliseconds. And hence this system is more efficient for charging, because the only thing what is expected in a charger is, depending on to the C rate, it has to charge, and the time of charging is more important, and the load, it has to be at constant voltage. So this was a validity for our charger. These are some of the voltages for different load conditions. This is for when the load is varied, what exactly is the output following the input, and at the same time, what is going to be the peak. So it was observed that the peak was being maintained within the specified limit, and the time of response are also very, very small. when compared to the other converters. This converter, whatever is used here is DAB, dual active bridge. So it has an input bridge as well as an output bridge. So this converts DC of one form to the other form. This is whatever is shown in this particular slide is the PWM technique, what is being derived for the MOSFET IGBT as well as for a silicon carbide device. The MOSFET and the IGBT was being replaced by a silicon carbide device. All these three circuits, the circuit remains the same, only the switches are being replaced and each driver circuit is different. So we have a PI controller, and from the PI controller output, we are deriving out the pulses for the two switches in the sense 4 switches of 2 cycles of for the DAB. This is the hardware waveform which has been obtained. We could see 4 different waveforms where 2 are in sync with each other. First and the third is similar, and second and the fourth is similar. And there is a dead band between both of that is also being taken care. This is the efficiency plot for all the 3 switches which has been taken up: silicon carbide, MOSFET and IGBT. And you could see that in silicon carbide, the efficiency was from 95, it starts out to 98. And IGBT was somewhere around 65. So it's obvious that when for the same circuit, when IGBTs are being replaced, IGBTs are the conventional devices which are being used in the circuit in the current real time. So if it is being replaced with the silicon carbide devices, the efficiency goes up higher. So this is the plot which tells us how say efficiency increase is automatically at the rate of losses. So the losses was being calculated, and the corresponding cost of the devices with respect to the cost of the devices is being plotted. Obviously, the cost of silicon carbide is more. That is on current day, but in due course of time, those rates also would come down. But with respect to efficiency, silicon carbide is more efficient than IGBT, but IGBTs are cheaper. So this is a plot which tells us loss analysis of silicon carbide, MOSFET and IGBT. This is the hardware setup. You could see our TMS kit over there with the loads, the power circuits. So as told earlier, a power electronic systems is being shown in this particular thing, where we will have different types of energy changes. We could have a distributed energy at the input, which could be solar, wind, or fuel cells, and the output of these particular distributed energy sources would be DC or AC, and hence we needed a first power converter which could be AC to DC or DC to DC converters, and the second one which would be a common converter which converts common base voltage of DC to AC. And when you're talking about AC, we will definitely have noises, and hence a filter is being added over there, and then the corresponding output is being connected to the point of common coupling where the other loads are being connected. So this is the role of power electronics in the smart grid. It converts one form of energy to the other. It maintains voltage, current, voltage, frequency and synchronization, and it also helps in bidirectional energy transfer. There was 2 different works conducted by my PhD scholar. One is with solar with uncertainty, and the next is with wind with uncertainty. And we have tried implementing AI ML techniques, and the techniques used is being listed over here. Autoregressive, SVM as well as LSTM was being used. And for electric vehicle charging data was being taken up from Caltech University's data. So with that particular thing, EV charging from solar with uncertainties was being taken up, and the results have been given in the next slides. This is the data what is being taken up for a holiday day, which is on a Saturday, January 6th, and the other thing is on a working day, which is on 16th. So you have a different patterns of solar requirement over there. So, and the above said 4 techniques were being taken up, it was being trained up, and the results for the same would be shown in the next slides. So the uncertainty of renewables was being taken into picture. So these are the predicted values. As you could see over here, this actual value, Sarima, SVR and LSTM is being given over there. And LSTM was being performing better when compared to the other methods was being considered. The ordinary methods of whatever we talk about doesn't take it up any uncertainty over there. Uncertainty or the disturbance and the different patterns of per year. We would be having winter season, autumn or summer seasons, etc. So the power consumptions would be different for each season. So all these things put together has been taken up for analysis. So this was the total confidence band which is being plotted for a winter season alone. Each season was being taken up separately, and the prediction for the same is being obtained, and the confidence level is being listed out there. And this is for the other technique for wind speed, which is with SVM, LSTM, and GRU. And you could see the output what we have obtained over there also. These are the wind speed predictions which has been carried out. The work has been given at the bottom, the citation, so that you can refer out for those outputs, and the details of the works would be taken up in the paper itself. So here the work was to forecast the power for solar and wind with uncertainties. So for the different seasons, and for the different time durations, and for working days and for holidays. So this is the overall smart grid, how exactly it looks like. You have a power generator, you have a wind system over there, which has been connected to the common smart grid through a HVDC systems or a UPFC. UPFC STATCOMs are power electronic devices which are trying to maintain the power, and the power quality is being maintained through these equipments. We have already detailed this particular thing in the previous slides. So these are some of the solar based connections of a power electronic with power electronic usage, how exactly it has been converted. You can see a series of PV arrays being connected in series and then in parallel. So a constant DC voltage is now to be converted to an AC signal. So a single inverter is being used. Since a single inverter is being used for all the whole PV array system, it's called as a centralized PV system. Again, the role of power electronics is the one which connects the renewable energy to the grid over here. So that this brings an importance of power electronics devices. And I have a series of connections which helps us to identify the importance of power electronics in renewables. This is a different configuration where we have parallel strings, and each strings has an individual inverter. You can see a set of PV arrays which are connected to an inverter, and the second module also has a set of PV arrays with connected to an inverter. These two are paralleled and then connected to a grid over there. So this is a configuration where we have panels in strings with individual inverters. This is with multi-string configuration, where only DC-DC converters are there initially. One common inverter is being given over there. In the previous configuration, each and every paralleling device had an individual inverter. The main drawback of that is the cost of the system increases, because many number of inverters is required, so the cost of the system increases. But the advantage of the previous system would be, even if one of the paralleling device is failed, the other would take up the load. But here, if the main inverter fails, then the whole system would not be able to feed anything to the supply. This is a detailed configuration of a single phase system, where a PV array is connected to a bridge circuit, where it has been DC is converted to AC, and it is filtered through the LC filter and then connected to the utility. So this is this bridge connection tells us how exactly it works out from DC to AC, an inverter circuit. In the previous diagram, we had it as a box. Here it is being explained with the bridge circuit. So similarly, we have many modules like that. Each and every PV module could have an individual inverter or a common inverter, depending on to the application and the reliability. These are some more examples which gives the details about the circuits, just to give a feel of power electronics. How is it used in integrating a renewable energy to the grid, and hence maintaining sustainability. So we have a DC to AC converter, which would be an input bridge as well as an output bridge, and that has been again inverted and then given to the supply. The main drawback of this particular thing, this has two things in parallel to maintain the reliability. Even if one of the system fails, the other system would be working. The only drawback in this particular system is you have many stages of conversion, AC to DC, DC to AC, and AC to DC. So many conversions, automatically the efficiency of the system becomes lesser. This is the control technique which is normally used for controlling the devices. It definitely involves PI converters with current, power, and reactive power being maintained at a constant value. So normally constant current control is preferred for smart grids. Moving on to the next renewable energy source, which would be wind. Wind has many motors being connected over, many generators connected over there. And this particular diagram shows a cage induction diagram, which is connected to a wind turbine. And the output of the generator is directly fed into the utility. When this source is intermittent, when wind energy is intermittent, then there will be a more flow from grid to the wind energy systems, which is to be avoided, and hence we have a reactive compensator which takes care of these things. These are the next 2 or 3 slides would be having different generators over here. So this is with synchronous generator. The previous one was with double gauge induction generator, doubly fed induction generator. And the power electronic devices used for connecting these generators to the grids have been given out. Either it would be a rectifier or an inverter, and the detailed circuit diagram of the same is being given over here. Depending on the power levels, it could be single phase or 3-phase. If the power level is greater, then we go in for 3-phase. Otherwise, it is single phase circuits. So these are some of the circuits which helps us to identify how power electronic devices are used in interfacing wind energy to the AC grids. So the system as is shown over here is a complex system. It has many number of switches. So controlling the switches is the major task to maintain the voltage or power in a constant level. So this is again one more circuit diagram for connection of wind to the grid. And this is along with the controller part, which again involves like solar controller, whatever has been explained. Here also we have PI converters, which is used for controlling the power, active power, reactive power, and to maintain, since it is AC, we have to maintain the phase sequence also. And hence a PLL would be used for blocking the voltage. So these are some of the circuits which are helpful for inverter circuits, and this is the common configuration which has been seen. We have both DC as well as AC into the system. The first thing we could see over there, AC is connected to through a distribution transformer where AC loads are connected, and this AC is being again converted to DC, and that has been connected to a DC bus. And from the other end, all the renewable energies are matched to this particular voltage, DC voltage, and either it could be a source. These renewable energies could be a source, or if the source are not available, then AC could be converted to DC and still being fed to the DC bus system, where the DC bus systems are connected to the DC loads. Nowadays, many different DC systems have been come into picture. We were talking about HVDC, and now we have small level, large scale level, medium level DC systems which have been talked about. And these are the controller circuits which have been established for controlling the SVM. This till now we have seen solar separately and wind separately, but a normal system would be having both solar, wind, as well as the load systems connected. So this is one of the example of connecting a wind system. So the wind, when something is connected in parallel, obviously we know that the voltage levels as either to be in DC or in AC. It should be of the same form. But the output of PV is DC and the output of wind is AC. And hence we are converting it into a common form, which is DC. So solar voltage is boosted or bucked to a common DC voltage, whereas the wind turbine, it has been rectified. The output voltage of the wind turbine is rectified and maintained with the common voltage, and that common voltage is taken to a 3-phase inverter, inverted and then connected to an AC grid or the load system, which is AC in nature. So this is the common things. So the same to the previous diagram, we have 2 wind energy sources connected to a common grid systems along with some power electronic based system to maintain the voltage reactive powers. This is the same connections with respect to a bus structure, because in electricals we always talk about IEEE bus system, 5 bus systems, 37 bus systems, 74 bus systems, etc. So bus system comes into picture. So here, for a double transmission line, in the middle, when renewables energies are being connected, you have two sources which have been connected at the extreme ends of the AC buses, and in the middle you are trying to connect a solar array into the system in the middle. So this is a pattern to show how renewables are connected in a bus system. So this is the things whatever we have talked about before. Either any of the solar should have to be converted to a common bus voltage, either it is DC or AC, and it would be feeding out DC loads when it is DC, and then inverted to be connected to an AC grid or to feed with an AC loads. So these are the things where innovations are still happening, and we have more areas for research. AI and ML to be brought into all the control techniques. Modular devices is more important, and replacing the lost devices with lossless devices like silicon carbide and gallium nitride. So this is the overall circuit with controllers. So power electronics. So we have stated till now how power electronics is being used in renewable energies, integration with the grids, and thus maintaining sustainability. So the real world applications would be microgrids, hybrid power plants, smart homes with IoT's things. All these are showcasing the successful implementations of synergy between your renewables, power electronics, and smart grids. And the challenges still being the sensors which has to respond properly, and security of the data, because cyber security issues are there with the interconnected grids, because it has been intelligent over there and it is controlling by itself, and hence cyber security becomes a major issue over there, or it's a major area of research which has been happening nowadays. Standardization and regularity barriers are there, because solar has a different standards, wind has a different standard, grid have a different standard, and pricing of this particular energies also is a great task. So cost and standards is one more thing which is a challenge, and these are developing techniques, and hence R&D improvisations also, or educating people also becomes a major difficulty. Future trends, the buzzword of AI should be there. So AI and ML into smart grids is more important. So AI and ML, what could it do? It can just predict the energy. So as we have shown in one of our work, it could predict the solar energy, what it could be there tomorrow, irrespective of the wind condition or the weekdays or weekend condition or wind. Prediction of wind, prediction of EVs as load prediction is also important. So any prediction should be possible with AI, and when this has been predicted with IoT devices, we would be able to transfer switch on those powers from the sources and transfer it back to the load. So IoT is also the next trend which has been taking up in smart grids. And blockchain, as we have talked about security and cost involved in renewables, power transfer, as well as for electric vehicle charging. Blockchain is one more area where future trend is trending. We have newer energies like green hydrogen and battery based technologies coming into picture. So that is also the advanced area where research can be taken up. So sustainable energy is a cornerstone of global development. So these are some of the things from here on. It will be some of the works which is being carried out from our BTech, MTech students. We have Amrita seed funded lab, which is autonomous e-mobility lab, which takes care of all the renewable based energy transfer into electric vehicle battery management systems, or drive based systems of electric vehicle. So in future, if there is any collaborative work, this would help others to contact us for further details. So these are some of the, because the buzzword is AI ML. So these are some of the works taken up by my PhD scholars and MTech scholars to predict the faults in the system, because fault prediction is more important. So fault prediction was being taken up with machine learning and DL technique, and electric vehicle load demand prediction was one of the work, and the other one is fault prediction with comparative study. The second one is deep neural network with IoT based smart systems for energy predictions and thefts, and the third one is the challenges what electric vehicle is been facing, when it is connected to the grid. So these are some of the works with respect to the current smart grid topic of study. And the same thing from electric vehicle point of view, we have a BMS coming into picture, battery management system. And the same battery management system is not going to be applicable for a UAV. So these two things were being studied. One for a vehicle which is on road, and one for UAV was being studied. And the different AI models for predicting the SOH of the batteries was being taken up. And the other technique is, when a battery is being taken up, balancing of voltage of the battery is more important. And hence we took up a study which is with passive balancing of batteries. That is the first work, the hardware setups shown as such. And the fourth work is about regenerative braking. There is much energy in the wheels of the electric vehicle, and hence regenerative braking energy tapping out and storing out in the battery is more important. That work is also carried out with AIML. So these are some of the works by BTech students for predicting SOC, SOH, RUL, state of charge, state of health, remaining useful life of a battery, with the ordinary ML technique, DL technique, and more extra to this particular thing, we have used hybrid technique, which was performing better than the ordinary ML and DL techniques. So these are some of the faculties who are working out, and the outcomes of our tag, which is thrust area group e-mobility. We have some of the so this is about wireless charging. And in wireless charging, we have done a 500 watts charger. And this 500 watts charger was being tested for different resonant conditions. So these are the outputs. And it was found that LCL resonant was performing better than the other resonance, because that was giving us more efficiency than the other resonance. Corresponding hardware outputs, and the hardware is being shown over here. Different topologies has been compared, and one topology was being suggested. The same topology was taken up with AIML as well as with fuzzy logics controllers, and the corresponding outputs are shown in the next 3 slides. This is a circuit. The outputs obtained for different load variations. This is a multi-output converter. Multi-output converters are playing major roles where more than one output is required, and hence this multi-output converter is being again controlled with fuzzy logic techniques. The other one would be balancing of battery voltage, what has been taken up, which is called as active and passive balancing. This is one such work. The other work which was submitted for PEDAS would be vehicle to vehicle, because when electric vehicles are there on the loads, last mile connectivity would problem would be there, or range anxiety would be there. So when there is a shortage of power in one of the source, then you could charge it from the other vehicle itself, which is with V2V technology. So this was one of the topology which was suggested for V2V. And there are many other optimization papers which has been taken up for selecting the chargers, where exactly EV chargers has to be placed. As per the Indian government rules, on a highway, 10 kilometer once, on either side of the places, 10 kilometer once you should have a charger. But to place that particular thing, it involves more studies. So that is being carried out, and this by optimization techniques. And in the due course of time, we would be dependent on to swapping, ma'am. Battery swapping will be one area which would be coming up in future in India. And hence, where should this battery vans be placed? What would be the minimum optimal distance it can travel, etc. is by the next work taken. As I told about power quality issues, when you are bringing in an electric vehicle or a solar or a wind to the grid system, automatically the power quality of the system decreases. You could see that in the waveform over there. Initially, the inputs is input current is following the input voltage. But when these things are connected, you can see that red color, you have distorted waveform. This totally distorts the total power of the grid, and hence to maintain that, we have to bring in power quality correctors. So that was being taken up, and the filters was being designed for this particular network. For a given network, the filters was being done, and it was being compared in this particular work. This is the overall circuit diagram of the same, how exactly it is connected, and the control technique what has been used over there. And this study was a review of electric vehicle with coordinated and uncoordinated charging. This is for BMS, battery management system. What are the different mathematical models available? So finally, we have analyzed and we have come up with a solution that 2RC model of a battery is best suited for any electric vehicle applications. And the same is being taken up for passive balancing. For initially for the passive balancing, if the cells are new cells, then passive balancing was found to be better from our experiments. And if the cell is old, it is as it is aging, active balancing enhances its life than passive balancing. So that was the conclusion of the thesis work of one of the student. The remaining slides would be for a regenerative braking. Depending on to the brake applied, the amount of force given to the brake, the total regenerative energy obtained to the battery is maximized, starting from the basic PI techniques, fuzzy logic, etc., and optimization techniques. All these are for regenerative energy based works carried out by my students. For fuzzy logic and ANN, these are the outputs, and ANN was performing better. These are the outputs of the batteries. The overall comparison table for ANN and fuzzy logic controllers for the regenerative energy, what has been tapped in. So the same thing with optimization technique, it gave better results. So the next work is with optimization, and the corresponding outputs have been shown in the remaining slides. Normally, when an electric vehicle is taken, we have different drive cycles. This is one of the drive cycle which has been taken for our study. Because when there is an acceleration and deceleration, our electric vehicle has to follow it. So this was the drive cycle which was taken for our study. And the amount of regenerative braking energy, what is being tapped out, is being shown here. The corresponding brake force is also there for both ANN as well as for fuzzy is being listed. This is the overall thing for comparison between fuzzy and ANN. Fuzzy had recovered more power than ANN, 200 watts more than ANN. Again, the same thing with optimization techniques. Drive cycle taken, its corresponding regenerative energies, and a comparative slide. So this is the flow in which where I tried to incorporate renewable energies, power electronic devices with smart grids, and how they are working out with sync was the main idea. And the works carried out related to these things I have tried to point out. So that's from my end. If there is any questions, I would like to take it up. Thank you, Sunish sir.
Most welcome.
Any
Yes,
doubts
sir.
from the audience? Any questions? Okay, thank you, ma'am, for this session. On behalf of all the participants and College of Engineering, Mutatra, I express our deepest appreciation for taking time to share your knowledge with us. Thank you, ma'am.
Thank you. Thank you, sir. Thank you for this opportunity. Thank you all.
Thank you.